Good morning, students. In last lecture we have studied about definition of complex number, then physical significance of different operators, that is j, j square, j cube, j raised to 4, graphical representation of complex number. Now next point is use of complex number in solving series LCR AC circuit. So we have to also do the practical named as series LCR circuit. So at first inductor, that is L, inductor is L, capacitor C and resistance capital R, they are connected in series across alternating EMF. So inductor L, capacitor C and resistors R, they are connected in series across alternating EMF, and I is current flowing through the circuit. Now alternating EMF is given by E equal to E0 sin omega t. Alternating EMF is given by E is equal to E0 sin omega t. Say this is equation number 1. Now equation 1 can be represented as E is equal to E0 e raised to j omega t, and we know that expansion of e raised to j omega t, that is cos omega t plus j sin omega t according to rule of mathematics. So according to complex algebra in mathematics, e raised to j omega t is cos omega t plus j sin omega t. J sin omega t is an imaginary part, cos omega t is a real part. In this equation, real part, that is cos omega t, is absent, and in this equation only imaginary part, that is j sin omega t, is present. Now as inductor L, C and R, they are connected in series, then we know that in series current is same, that is I. Now let us suppose that VL be the voltage across the inductor, VC voltage across this capacitor, and VR, that is voltage across resistance. So VL is voltage across inductor L, VC voltage across capacitor C, and VR is voltage across resistance R. Now in terms of complex number, these voltages are given by, that is VL voltage across inductor, that is by using Ohm's law, that is VL is equal to XL into I, in terms of complex number j omega Li, j omega Li. Then VC voltage across capacitor, it is equal to capacitive reactance XC into current, and in terms of complex number, that is minus j 1 upon omega c into I. And finally by using Ohm's law, voltage across resistance VR, that is equal to resistance into current. So these are the three different values of VL, VC and VR. Say it is equation number 3. Now the total voltage in the circuit is the sum of voltage across inductor L, voltage across capacitor, that is VC, and voltage across resistance, that is VR. Hence I can write total voltage, say capital E is equal to VL plus VC plus VR. Put the value of VL, that is JWLI. So JWLI plus value of VC, that is minus J1 upon omega C I. Minus J1 upon omega C into I. And value of VR, that is R into I. So we get the new equation, that is E is equal to J omega Li, then plus into minus J into 1 upon omega C into I plus R into I. So take capital I common from all these three terms, and also take J common from these two terms. So we get total voltage, that is E is equal to, first I is common from these three terms, I can use the curly bracket, then in this term remaining is omega L, in this minus 1 upon omega C, then I have taken J common from the first two terms, so I can write here J, then common is I from three terms, and here we can write remaining term, that is plus R. So we get E is equal to I into curly bracket J omega L minus omega C plus R. Then we can write this equation, E is equal to I as it is inside curly bracket, J as it is, omega L, that is, it can be written as XL, that is inductive reactance, XL is equal to omega L, and capacitive reactance XC, that is 1 upon omega C. So 1 upon omega C, that is capacitive reactance XC, plus R as it is. Now say this is equation 4. Now we can compare equation 4 with standard form of the Ohm's law, that is E equal to IR. So the quantity, that is R plus J into XL minus XC, R plus J XL minus XC is called impedance of series LCR circuit. The quantity R plus J XL minus XC is called as impedance, that is complex impedance, and impedance is nothing but total resistance offered either by L, that is inductor L, capacitor C, or resistor R to the flow of AC current I. So this is called as complex impedance, denoted by letter Z. So Z is equal to R plus J XL minus XC. It is called as complex impedance. Z is called as complex impedance. And we can define impedance: total resistance offered either by inductor L, capacitor C, or resistor R, or both L and C, or both C and R, or both the three components, all the three components, that is LCR, to the flow of AC current is called as complex impedance. and its magnitude is given by Z is equal to square root of R square plus XL minus XC bracket square. So next part we will discuss in the next lecture. So we can stop here up to the equation 5, that is magnitude of complex number Z is equal to square root of R square plus XL minus XC bracket square. So listen here once again. We are going to solve AC circuit by using complex number. So at first, inductor L, capacitor C, resistance R, they are connected in series across alternating EMF, that is E equal to E0 sin omega t. Now voltage will produced across each component. Let VL be the voltage across inductor L, VC voltage across capacitor C, and VR voltage across resistance R. Now we know that in series current is same flowing through each component, that is I. Then alternating EMF E equal to E0 sin omega t, equation 1. Equation 1 can be written as E equal to E0 e raised to j omega t. In equation 2, real part is absent, that is cos omega t, and imaginary part is present. If you take expansion of e raised to j omega t, expansion of e raised to j omega t is cos omega t plus j sin omega t. Cos omega t is a real part, it is absent, and j sin omega t, it is imaginary part, it is present. So we can write E equal to E0 e raised to j omega t. Now according to Ohm's law, voltage across inductor, that is VL, is equal to inductive reactance, that is XL, into current, and in terms of complex number it is JWLI, so J omega Li. Then the voltage across capacitor VC, that is product of capacitive reactance into and current. So voltage across capacitive reactance, that is VC, is equal to product of capacitive reactance XC and current I, and in terms of complex number minus J 1 upon omega C into I, and voltage across resistance according to Ohm's law, V is equal to IR, or say VR is equal to RI. Let me give this common equation as equation number 3. Now total voltage is the sum of voltages across each component. So total voltage is E equal to VL plus VC plus VR. So total voltage E equal to VL plus VC plus VR. Put the value of VL, that is J omega Li, plus value of VC inside the bracket minus J 1 upon omega C into I, bracket complete, plus VR, that is Ri. Now take I common from all the three terms. Left hand side E equal to as it is, I is common. Use the curly bracket, write the remaining term. In the first term remaining is omega L. Also have taken J common from first and second term simultaneously. So J is common. In the first term remaining is omega L, minus in the second term remaining is 1 upon omega C. Then bracket complete, plus R is it as it is, and I is already taken outside the bracket. I is all taken common. So EMF or total voltage E is equal to I into curly bracket J small bracket omega L minus 1 upon omega C, small bracket complete plus R, and this curly bracket complete. Now omega L can be written as XL, that is inductive reactance, and 1 upon omega C can be written as XC, that is capacitive reactance. So put omega L as XL, 1 upon omega C as XC. All the remaining term as it is. We get new equation E is equal to I into curly bracket J XL minus XC plus R. Say this is equation 4. Compare this equation 4 with standard form of the Ohm's law, that is E equal to IR. Comparing, we get the term that is R plus J XL minus XC is called complex impedance, that is Z. It is denoted by letter Z. Z is equal to R plus J XL minus XC. It is called as complex impedance, and magnitude of complex number, that is Z, is given by Z equal to square root of R square plus XL minus XC bracket square. So this is about up to the equation 5. Next part we will discuss in the next lecture. So let us stop here.